So welcome everybody. Thank you for joining on time. We always aim to start on time and finish on time at these events. We're trying a new system today. We're running this on Teams. In the past, we've used Eventbrite and MailChimp to register. We decided to try Teams for today, and it seems to be working well. Hopefully there won't be too many teething issues. And you've got a different invite by a different mechanism as well this time round. But that seems to have worked quite well, which also automatically generates an invite into your calendar. So we're just trying to improve things. So give us your feedback, give Dishu your feedback in case you had any technical issues joining today. Today we're going to be talking about automotive post-event, the presentations will be available on the DV Club. Okay, I think I may be sharing the closing slides rather than the opening slides. So today we'll be verifying safety in automotive, as I mentioned. Thank you to our sponsors, Agnesis, Cadence, Brecker, who will all be speaking today, Synopsys and Tessolve, who host this event. Also, we have ARM and ST, who are our location events, although we're not actually running at locations today. Today we have 151 attendees, all remote, representing 89 companies in 32 different countries. Okay, and here's the agenda for today. Hans Leo Ross from CPS Safety Academy will be kicking us off. He's a safety expert. He's going to really set the context and explain a little bit about some of the verification challenges. And then, as I mentioned, Brecker, Cadence, and Agnesis will be going through some solutions that we have for trying to verify functional safety in the automotive ISO 26262 space. Okay. And so before we go on, I think we're going to ask Leo, Hans Leo, to share his screen, and then I'll do the bio for him. Disha?
Yeah. Hi, Leo.
You need to give him permission to present.
Yeah.
Okay, thank you very much.
Do you want to share your screen, please, Leo? And then I'll do an introduction.
Yeah.
Hi.
Hope it works well.
Yeah, we can see you.
Yes.
I'll do the introduction and we'll let you start. So our first speaker today is Hans Leo Ross. He's from the CPS Safety Academy, where he's managing director. And his title of the talk is Verifying Safety in Automotive. He started as a project engineer in oil and gas industry, storage, transportation, and automation for pipelines, refineries, chemical plants, ship, rail, onshore and offshore. Since 2003, he's worked in automotive industries, various positions at Continental, Mando Europe, Bosch Engineering, and Robert Bosch. The highlights of his career is head of German working group for the ISO 26262, head of safety in Continental and Mando Europe, a lead architect for safety. System safety for e-mobility, fuel cell, and hybrid solutions, development of base concepts for OTA, SUMS, automated valet parking and infrastructure supported IAD. For the last 2.5 years, he's been director and advisor for safety for remote driving solutions in public road traffic. He's the founder and managing director of CPS Safety Academy and publication of various books in the field of safe mobility solutions and many patents with solutions for the upcoming safety challenges. He's located in Germany. So over to you, please, Hans.
Okay, thank you very much, Mike. Yeah, first of all, I'm speaking today as behalf of the managing director of the CPS Safety Academy.
Okay.
And the CPS Safety Academy are, let's say, a group of specialists who try to improve and to develop all that safety knowledge which we need in automotive industry, but also in other industry, and combine our knowledge somehow, and of course provide therefore training and education to all the people in the outside world. Unfortunately, we are very German people at the moment, but we are really open also to go at the end with partners from abroad of Germany. So, but I'm coming quite soon to the contents, and I want to give you, first of all, a little bit background why I'm coming to that topic to you as a specialist of verifications. And yeah, I'm starting with legal regulations. I think in the 1968, we start already with definition in forms of regulations for homologation, that we need certain equipment in the vehicle, and it start with seat belts and end up with electronic devices. So, for example, very important for electronic, the VDR EGAS approach, which then also became somehow a background for the Annex 6 of the UN 79, which is known as the electronic annex. So that means how we solve with electronic solution in vehicle control. And in 2005, we start with the development of ISO 26262. And now we are preparing the third edition for ISO 26262. And a very interesting view, especially for verification and all that topics for today, it's the publication of the Automotive standard, and I'm coming deeper to that later on. One important thing is also legislation. I think we are here verification, but one major topic became transparent when we start here, that the validation topic needs a wider room, because most of the regulations were just compliance to the requirements that we have, but they realized that that is not sufficient. So Working Group 29 defined a 3-pillar model in order to make several different solutions, how to provide evidence, for example, especially for automated driving functions, but also other functions where we have to deal with uncertainties. And one of these major examples where they give that we cannot just with physical tests or technology tests prove that systems working is when pedestrian at the end move between parking vehicles, and parking vehicles are not that structured that we can perceive that with technical devices. And so there is a huge scenario of test scenario, and the development of test scenario is necessary. So there is not only real world tests, so there are also audits and process necessary to assess in order so that you get proper simulation, and to provide also the evidence that its simulations are adequate structure for that. Unfortunately, when we developed ISO 262, we had a lot of exemptions in it. And you see here a small sketch how we at the end need to deal with those exemptions. And yeah, and we have to find also solution in order to avoid accident in public traffic. I think one of the most critical points is at the end when we're talking about the limits and the typical behavior which derived out of the vehicle dynamics. So we have here huge functional dependency which go in longitudinal and lateral management, and especially the actuators like brake and steering system have sensitive control circuits in order to make sure that you meet all that requirements, so that especially in a very dynamic driving situation, you are still able to control the vehicle. I think major topic was when we developed ISO 262, you see at the end, I made it a little bit orange, and I have the 2011 version here for you. But we had the focus really on verifications. So we mentioned particular that we need to verify the requirements. And we had just one small element which called validation, safety validation, which we're addressing on vehicle level, that we have also to do some validations. In 2022, then ISO 21448 had been published, and this SOTIF is the abbreviation for safety of intended functionality. And here, of course, we get a significant focus, not only on verification, we get it only on validation. And I also go through some slides quite quickly, but you will get it in the handout, those slides, so that you can read the details, because there are some think it's challenges necessary to consider them. First of all, when we're talking about safety of nominal performance, we see at the end that we have inadequacy and insufficiency. And insufficiency could mean at the end wrong functionality. It could mean at the end wrong situational context, wrong operational condition, environment, control application is not sufficient. And also that we have really low performance and different characteristics for that one. And unfortunately, ISO 262 said to us, this document does not address the nominal performance of EE systems. So what we should do in order to provide evidence is that this impacts also not addressing any issues which lead to public accidents. Yeah, I think when we looking the basic engineering flow, I use another representation as it had been done by ISO 262. You see already that you have, first of all, a basic flow of planning, feature development, function concept, functional design, robustness, realization, and then the integration. And you see on the V model, it's not a typical, here is system, here is a component, and here is the technical realization. You see that they have an intended purpose, that we have an operational environment, that we have here a technical risk management, which lead at the end to product assurance. And you see also that we need a functional model within its boundary, that we have a behavior model and environmental model, design model and implementation model to see that all the different domains from the design to testing and also to implementation, make sure that we then later on during the integration process doing the right verification and validations. As you see, when we developed first vehicles, starting from the Model T to a VW Beetle, etc., we saw that mainly the vehicle was dominated by mechanical parts. And here's a little bit an explosion. When you see here in the vehicle, you see here the front axle with the steering devices, etc. And then you have a lot of mechanical devices which make the functionality and ensure the functionality for the vehicle. And this physical view, unfortunately, is today not sufficient to consider such an application and to assess really if our electronics and our software are working correctly. When we convert then to hardware, and I learned at the end, more or less you in the audience are mainly hardware experts, we see also that we need a similar architecture and hierarchy in our structure so that we have here a vehicle level, a system level, a component level, a realization level. And on the realization level, you see then the circuit diagrams, how we see our resistors and elements. We see a signal flow on all that 4 levels, for example. And here we can start to assess and validate if our requirements are the correct requirements, and of course verify that our requirements are fulfilled by the implementation. In automotive industry, I think especially when we are on this lower level, we have those robustness testing. I think the major domain is LV 124 and LV 148. By the numbers you see already that it was dominated by the electrical power network, which we have in a vehicle. So in passengers car, we have typically 12-volt system. In lorries, we have typically 24-volt. And we start also to standardize on a 48-volt board nets for hybrid vehicle. But that had, due to the discussions about hybrid benefits, etc., had been stopped. And today there is also a LV 400, etc., available, for example, for high voltage systems and even greater voltage level. And this is not really a public standard. It is more or less broken down into the typical brand standards or OEM standards. For example, Volkswagen 80,000 and Mercedes-Benz standard LV 100 is the same name. So the origin comes from Mercedes-Benz. And for example, in BMW Group standard as well. Then you see already the typical test. You see already these are also not the typical hardware tests where you just purely start the hardware. but you have also to see, when you see here energy recovery, start pulse, short interruption, reset behavior, etc., that there are already system tests involved, and these are also to assess really the hardware. Not only hardware tests are sufficient, so that we have to do system tests in order to assure really also basic hardware criteria of the element. I think we already had a few on discrete elements. When we make that here, I try to make that breakdown a little bit for a standard microcontroller. And in a standard microcontroller, we have, even in silicon, quite a lot of functional groups. And here, this is not the realization of the silicon. This is just also functional groups, which we see, which have different functions in such a microcontroller, which must be combined and, of course, used in a certain context in a different applications. You see here, for example, when here we have those functions which are typical core function, which are very close to software function. And we have also typical functions which are dominated to bring the outside world and the inside world together. And that is connected by internal bus, crossbar, or however you want to call that. Of course, sometimes when we go in automotive and in safety application, we are quite often using single core lockstep. In this case, we have just 2 cores, and maybe one core is dominating and the other is just as a shadow mode working. Or we have really also multi-core principles in somehow a lockstep principle, where those boss cars at the end are connected to the internal bus and could write and read from the I/O and the outside world, and could also have independent connection to the operating function blocks in the system. What we typically do is, for example, when we're working in a single core lockstep, or in general in lockstep, we have a core 1 and a core 2, which are comparing with each other. And when the comparison is unequal, yeah, we quite often go to a shutdown and degrade at the end the entire microcontroller. This is at the end, to keep a system under control, very questionable. And when we go also here to typical analysis of software elements, we see that we have quite a lot of parameters which influencing the correct behavior or the correct functionality of a software module. There is really the input and output, which are mainly often used in the safety analysis from software, but the configuration, the time assignment, the resource assignment by scheduling, etc., and so on, are also major sources at the end for incorrect functionality in the software. So now we're coming to the hierarchy, where we're coming all that requirements. When we have an architectural view, we need to have a neutral observer so that we see the vehicle in the road environment from a neutral point of view, so that we see in what relation is the vehicle to the different people in the environment, and we see their behavior, our behavior of our vehicle that we drive, and how is the relation and what derived really what kind of risks out of that. In order to get that more structured, there is, for example, SIE J3049 that propose us a hierarchy in the structure, how to structure that and how to bring that down. So they consider in the level 0 ground vehicle system, which control the vehicle, and then they break it down also to environment, driver, passengers, and the vehicle. And then under the vehicle, you will find the classical powertrain, chassis, body domain, and whatever HMI topics, until we break it down even to wheels and steering system and brake system. This is just one example, which I recommended when you have those issues to consider, because I'm addressing here some topics which are at the moment quite difficult to handle in the automotive industry. Usually the basic idea of ISO 262 was also that the upper level will be defined by an OEM, and he defined so-called item definition and the functional safety concept. And this functional safety concept would be spread to different tiers, and the tiers provide a technical solution, which we call the technical safety concept for the different devices. But one basic functionality, for example, like steering today, is not based just on one control unit. There are several control units available. And when we're talking about automatic driving, we see that we have a high electronic sensor set and that we have high electronic sensor fusion control device, ADAS control devices, until we go then on the classical steering and brake controller, which also cannot work according to the same principle like all these other devices. And of course, we have to validate that. But in order to validate that, we need to have significant information about the EE architecture so that we know, for example, the power supply, the placement, and also the way how they are connected and what is the runtime and the prioritization on the network and all that stuff. And if we don't consider those requirements and for our application, we're running into difficulty to assure, for example, that we can design and make here the in lower level decision in the right structure. We get on top that we not have only a functional safety concept, we have also to implement the basic functional concept for the usability. We have to implement an HMI concept. We're developing a TARA for the or threat analysis for the security measures. We have a SOTIF concept. We have, of course, the functional safety concept. And all that need to be integrated into one control unit. And we have to provide one solution for all that requirements which derived out of that heterogeneous structure. Then you see that you have a hell of scenarios in automated driving, which derive and define for different system and operating state, different conditions and different states to the system, where we find today quite a very interesting model-based verification approach, where we can see how the vehicle drives in different scenarios, and we can manage here the, of course, challenges here. And such an operational concept, of course, then need to address certain things. We have certain solutions before we can integrate and validate this technical solution. Typical, it is seen that we have, first of all, a logical context and a functional context, and we have to break that down and to provide a technical solution for that one. So we have one upper state, a functional and logical behavioral structure before we come to the technical solution. On higher level, you see that we have an operational design domain where we see the degree of freedom and how the vehicle is moving. Then we see, of course, the behavior of the vehicle inside that operational domain. Unless we're coming at the end here to one important thing, how we test that and how we validate all those things. So this huge set of standards is developing to find here verification measures and validation measures and to develop the right test scenario for those applications. For us, it's very important that the application is complete and that we also consistent and correct for that one. This is one of our key criteria. And for example, one method which is quite old, to receive observer characteristic, can give us some insights if our specification is correct or incorrect, so that we get here, for example, by the means area under the curve, if we're talking about true positive, true negative, false positive, or false negative. In real situation, we have a state machine. So we have steady driving, and steady driving lead in certain failure condition that we have to perform a minimal risk maneuver so that we come into a minimal risk condition, which is still an active function, which needs availability for the electronics. When we see a vehicle on the higher path, we see, for example, for such a control device like lateral or longitudinal control, that we have a lot of feedback loop for one time over the HMI, so via the driver or via the environment or any other interfaces that we have. But when we break down and don't see the context of that one, we don't see at the moment anymore the outside world. And when we are on a system level, we don't see all that interfaces anymore. And so you see, whenever we are on a different level and whenever the OEM does design decisions, whenever different tiers in different level making design decision before we here starting in the electronic to design this microcontroller, this microprocessor, or this FPGA, or whatever we use, we have a lot of verification and validation steps behind in order to assure that we have here the right requirements. So a breakdown and a verification is only possible if we know really the typical contents of those applications. And you see here in the example from a timing diagram, whenever we see a reaction and the device which at the end decide that we change, for example, from braking to an ABS situation, we at the end coming here to a very small element which decided if we brake, steer, or whatever vehicle dynamic function we do. And here there's, of course, a key question, how we verify, and can we verify all that by means of verification, or do we need at the end also other validation method? And the big question is when we, for example, here in a typical hardware level, how do we validate all that criteria which need in this intended use, intended functionality and performance so that we are able to make assessments if that is, for example, correct, complete, or consistent. Typical new application, not using any more embedded controller, we're going really to high performance computing devices. And we have here, for example, applications with virtual machines and virtual containers. And you see the hardware goes much far wider away from that. In the history, I already mentioned that we had an VDA AGAS approach. But today we have redundant controller which need to be synchronized and parallelized in time. And it is very important for them that we working here in closed and open loop solutions so that we coming here really to synchronize and really proper behavior of that PID controller in its given context. And unfortunately, AUTOSAR give us some ideas how we measure performance and how we monitor performance. But unfortunately, for all that safety mechanism that we need to assess, we need at the end really to break down what is the correct specification so that we can assess safety relevant features, functions and characteristics during runtime. Yeah, coming back here, mechanical is easy. But for example, in aviation technology, where they have similar issues, they going at the end not to fault injection over limit test, they doing also during integration, HAS and HALT, which give you the evidence about the possible integration. And so we're coming to our model that we have to do also in the specification and on our model, a lot of verification and validations, as already mentioned also in the legal requirements derived from the validation method for automated driving. And here, for example, typical software testing measures which need to be done because a microcontroller testing or an FPGA testing without the firmware or the software is nearly impossible. So we need to consider and that we go a step beyond, that we come up really with requirements-based testing beyond that one and coming up to really system. The old ISO 262 statement was system degrades from the defined state in case of deviation. And here we have now to assure that a certain function will be realized in the specified environment. And this is a very challenging situation. And yeah, I think legal requirements, the roadworthiness of vehicle, new technology, etc., have to provide new solution and sufficient transparent by requirements in natural language are nearly impossible. So we need a model-based approach. And we need to find solution so that we can realize really hard and firm real-time safety-related system. Thank you very much. I'm a little bit over time, but I hope you can excuse me. And thank you for your attention.
Thank you very much, Hans-Leo. That you actually bang on time, so it's a very good timing. Thank you very much. Unfortunately, we don't have time for questions, but what we wanted to do there, and hopefully that's helped, is just to really give the context for automotive safety. And I think we're privileged today to have an expert like Hans-Leo to explain that to us. And it really puts the context of the complexity of doing chips for the automotive and industry and compliant to ISO 26262. And now the next three speakers will be looking at the types of verification solutions that they can apply. So I will give you a virtual round of applause. Thank you very much, Hans-Leo, for covering that in such clearness and in such a short amount of time as well. I think it's set a very good context for the rest of the speakers. Thank you.
Thank you. Welcome. Thank you very much to the audience also.
Okay.